Good morning, everyone. Shall we start, or I see a few empty seats, so we should wait for people to arrive? Okay. So, what I gather from here is that as of now, there has been no lecture on ocean data assimilation systems. But before I start, all of you guys are from, like, what are your backgrounds? Like, is it somewhere from earth sciences, or it's a very general background? So
I think most of them have the atmosphere, ocean, I think physics background.
okay.
Yeah.
So I suppose you have a fairly a fair idea about oceans. Any case, we'll proceed and we'll see. So I come from an institute which is called Indian National Center for Ocean Information Services. So this institute, the mandate of this institute is very similar to what IMD does, Indian Meteorological Department. So they issue atmospheric forecasts, the weather predictions, and we are into ocean predictions. How the ocean is going to behave, both in near future as well as maybe a seasonal forecast, or even we are trying to also come up with decadal forecasts, like sea level rise, so on and so forth. Like you must have understood by now that data assimilation is a very integral part of any forecast system. So this is how I have organized my talk. So there will be a very quick recap. Just I'll highlight the most important points that will keep on recurring in this lecture. And then I'm not sure whether anybody has told you how to estimate observation error. So when you write that cost function, by now I'm assuming that you have a very good idea of that Kalman filter cost function. So in the Kalman filter cost functions, there are two variables. One is your model error covariance, and the other one is your observation error covariance, right? So in the next, I'm going to talk about how to estimate that observation error covariance. Did anyone talk to you about this? How to get this as of now? Anyway, then I'm going to give you an idea about the ensemble data assimilation system, which is LETKF here. And next, we'll talk about, is it always good to assimilate all the observations? Okay, so that's part A, and in part B, in the next lecture, we'll see how actually we can implement LETKF in the models. So I'll give you some tips on how to do that. So quick recap. So this one you are already aware of from the Kalman filter. So XA is the analysis, and then there's a background, and then the innovation is multiplied by this Kalman gain. Now, I pose a very simple question, is suppose there is a model that predicts the temperature of this room, and it has predicted something to be 31 degrees Celsius, okay? Whereas when you take a thermometer to the center of this room, it says 30 degrees. The question is, we are trying to go near to the truth, which is the analysis. So what is the analysis in this case? So this is a very simple. You just have to plug all this in to this and assume that the observation error covariance, which is, let's say, sigma 0 square, and the model error covariance, variance in this case, because it's a scalar, is sigma b square, then you can come at a very simple expression for your analysis. So what you see in your analysis is that your background and your observation, both of them are multiplied by some weight factors, okay? And in the asymptotic limit, that your model error covariance is much, much larger than your observation error covariance, what we see is that analysis approaches the observation. In the opposite limit, when your observation error covariance is much, much larger than your model error covariance, your analysis approaches the background model state. What does this mean? This means, so this sigma b and sigma 0, the two error covariances, this tells us about how much trust we are to put in the model background state or in the observation. So what this is saying is that when the model error covariance or the model error variance sigma b is much, much larger than the observation error variance, this means that there is a lot of uncertainty in the model. And I do not want to trust my model. Rather, I will trust the observations. So the analysis inclines towards the observation. In the opposite scenario, when there is a lot of error in your observation, you know beforehand, there is a lot of variance, there is a lot of uncertainty in your observation, the analysis will incline towards the background. In most common scenarios, what you will have this. Okay? Your model analysis will be a combination of your background and the observation, both of these terms multiplied by a weighting function. Okay? Okay. So just going back to the previous example. So we said that the model, so this is the analysis, and we say that the model came up with something like 31 degrees centigrades for the temperature of this room, and with a variance of about 2 degrees. So this green one is the distribution. It's a Gaussian distribution, right? With a mean at 31 and a standard deviation of about 2. For the observation, it is 1, the observation variance, and the mean is 30. So in this case, you can see the blue, the red line. The red line is much narrower than the green line, highlighting that there is a lot less uncertainty in your observation than in the model. And the blue line is your analysis, which is like if you plug all these 4 values into this equation, you will see that the mean is 30.33. That is, it has inclined closer towards the observation. So one was 31, the other one, the model was 31, the observation was 30. But since the error variance in the observation is less than the error variance in the model, the analysis has inclined closer towards the observation than towards the model. It is less than 30.5. Okay? Also, the error variance in the analysis is 0.8, which is less than both the model error variance and the observation error variance. Now the point is, suppose you keep on doing this, okay? What happens is this, your analysis error variance, this keeps on decreasing, okay? What happens then? When it keeps on decreasing, you come back to this slide. This keeps on decreasing means your sigma b keeps on decreasing. You are having more and more and more and trust on the model estimates, on the model backgrounds, right? With each assimilation cycle, your analysis error is decreasing, which essentially means that as time progresses, you are having more and more and more trust on your model estimate. The observation estimate remains the same. So what happens? There is going to be a time when your data assimilation system is simply going to neglect the observation. You will approach this condition. Okay? Right? Which we do not want. So in order to avoid that, what do? We do something like covariance inflation. After each assimilation cycle, this error covariance, this analysis error variance, we artificially inflate it by some factor. Okay? What that factor will be, that depends on some trial and error. Okay? But the question is, when is inflation not good? So there are times when you will have to be very cautious about using inflation. Look at this picture. So this is the Indian Ocean domain, okay? And these dots that you see, these are all the observations, okay? So at each of these observations nearby, when you assimilate, what do? You have an observation error variance, covariance, and the model error covariance, and the analysis that you get, that analysis error covariance decreases in all these locations. Okay? But what about this location? This red circle. Here, there are no observations. Right? But when you apply a covariance inflation, you apply it uniformly throughout, because that is easy to do. It's difficult to apply it in a spatial way, spatially varying way. So over here, if you keep on inflating, the model error variance keeps on increasing here without any mechanism to decrease it, because there are no observations and data assimilation does not affect this place. So the next time, if in future some observation pops up here, what will happen? Can't hear you.
Inflation will reduce that area.
No, before inflation gets reduced, the model error variance here has increased so much that the data assimilation here will have no trust in your model estimates. It will only trust the observation. Is it clear? You can always interrupt me and ask questions. Is this clear to all? Since there are no observations here, it's an observation sparse region, okay? And it has been an observation sparse region, let's say for 10 assimilation cycles. During each cycle, the model error variance is going to rise because of covariance inflation. I'm applying covariance inflation uniformly everywhere, okay? So after 10 cycles, the model error variance has become so large, okay, that when an observation comes here with its own observation error variance, the model error variance is so large that the data assimilation system is simply going to ignore the model estimate, okay, and will incline towards the observation by a large margin. What happens then? In situations like this, let's say the temperature here is 30 degree from the models. The observation tells no, it is not 30 degree, 26 degree. And then there is a sudden jump because in the analysis here by let's say 2 degrees centigrades. Because of data assimilation, the model jumps from 30 degrees to let's say 28 degrees. By 2 degrees, the temperature has fallen. It gives the system things called shocks, assimilation shocks. So there's a temperature decrease that will give rise to some anomalous sea level, okay, because of something called a steric effect. Okay? Steric effect is something that happens because of expansion of the water column, expansion or contraction. Okay? So a sudden rise or fall in sea level, what it will do, once it happens, it is going to radiate this shock throughout the domain. And how is it going to radiate? Through some spurious waves. Okay? And these spurious waves are then going to contaminate your entire domain because waves are not localized. It is going to spread out. Okay? So these are the things that we should keep in mind. These are some practical issues that we will face when we undertake assimilation in numerical weather systems or in oceans. Okay? So next, there is another simple example. The question is, what is the role of model error covariance? Anybody? If you know, then I will skip it. What does this P here? What is the role of it? Apart from this ratio that we have seen, this P and model error variance and the observation error variance. Apart from that, what is the role of P? Okay, so we'll understand this. So let's say I measure, again, temperature at the two ends of this room. Okay? Using, not measure, my model estimates the temperature at the two ends of this room at the two walls. One is x1b and the other is x2b. Okay? And the temperature that I observe is somewhere in the middle, here. So these are the two ends of this room, and y0b somewhere around here, I measured the temperature using a thermometer. So y0 is my observation, right? So again, we will try to estimate our state vector analysis. So now my analysis is no more a scalar, it's a vector. Okay, so this state vector is like a column vector. One is x1b and the x2b. Correct? Everybody understands this? Okay, so this is my state vector, and this y0b, so this h operator. So this, what will be this h operator? H operator will be alpha x1b plus 1 minus alpha x2b. Is this clear? So this one is alpha and this is 1 minus alpha. Okay? With this, I can figure out what my analysis is, analysis state vector. So you can analytically compute this and you can find your analysis state vector to be something like this, provided you choose your model error covariance, okay, which is anyway a symmetric matrix, sigma b, and then your off-diagonal elements to be some factor mu times sigma b square. Okay? With this, now, let's say that the model has independently estimated the temperatures of these two walls, which means there is no correlation between this wall and that wall. In that case, you have your this cross correlation to be 0, right? Your off-diagonal elements will be 0 because the dynamics of this wall does not affect the dynamics of that wall. Okay? And let's say I choose alpha to be 1, which means that I am observing only one of the walls. So my observation is at one of the walls, not somewhere in between. Okay? We have simplified the system. So once you have this, your mu is 0, your alpha is 1. Now you can very easily estimate your analysis of the temperatures of these two walls. One is sigma 1a is this, just like the previous scalar problem, and your other wall over here, that is simply is not affected by your observation of this wall. You have observed the temperature at this wall. Okay? Fine. Now let us say that the mu, there is some cross correlation between these two walls. Okay? My mu is no more 0, it's non-zero. Correct? When I do that and when I solve this, what do I see? And I still observe only one wall, the temperature at only one wall. Now you will see that the temperature at this wall is affected by your observation of this wall. So what does exactly the role of P? The role of background error covariance is to transmit information of observation from one location to other model grid points. Is this clear? So you are observing at a certain location. That information can be passed on to a distant place through P, through your model error covariance. Okay? So is this good to pass on information from one place to another? Yes and no. So this is a plot where it's a very simple plot. We have plotted analysis minus background for the Indian Ocean. So these dots that you see, these are the observations. Okay? But what we have done is that we have put on a localization radius over this, which means that we are limiting the effect of observation only up to a certain distance. For example, here, take this observation. The limit of this observation, the influence of this observation is limited only within this circle. Why is this necessary? Because unless you do this, suppose this observation, unless you put a localization mask, this observation will affect your model variable here, 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 everywhere. We do not want that. Because what is happening at a distant location does not necessarily affect what is happening here. Because you all have heard of correlation lengths, right? Correlation length scales. Okay? Suppose whatever is happening at the Arctic Ocean is affecting what is happening in the Indian Ocean. We do not want that, because this is beyond the correlation length scales of the dynamics involved. Okay? So that's the reason we should put on a localization mask, that I will allow my observation, whatever observation it is, I will allow my observation only to influence up to a certain radius. And how do you choose that length scale? Whether it is going to be 100 kilometers or 500 kilometers or 1000 kilometers, how do you choose that? Mostly by trial and error. Okay? And also out of experience, I will just tell you, you can note it down because tomorrow you might need it, is that the choice of this length scale depends on the resolution of your model. Okay? So if your model is of a very coarse resolution, let's say you have a model of 1 degree resolution. You understand 1 degree resolution, right? So in the tropics, it's like 110 kilometers. So your grid points are spaced every 110 kilometers apart. Okay? For a very coarse resolution like that, you need a larger localization radius. For finer models, for example, something like 1 by 12 degree or 9 kilometer resolution models, okay, you need a much smaller localization radius. In the system that we use, we have kept a localization radius of about 200 kilometers. Okay. In principle, what you say is yes, but then the problem is that the correlation length at each location is going to vary. Okay, and it's very difficult to estimate this correlation length. Like difficult to not estimate, to implement this in a realistic scenario. And also this correlation length scale is going to vary over time. So it's not that at one instance you have estimated this correlation length scale and then you forget about it. That does not happen. It also has a time varying, it varies across time. So that's why most of the practical data assimilation systems, they work with a uniform localization radius across space and time. It's easy to implement, and we do not lose much also. Because at each instant of time, if you need to find out that correlation length, it will be computationally expensive.
In principle, what is the process?
Process of?
Even if it's expensive, actually estimating these correlations.
So there is this you have to find out this radial distribution, and from that radial distribution,
From which?
so this is okay. So the point is for each of the variables, for temperature, salinity, etc., etc. So at each of these grid points, you will have to figure out the radial distribution of that.
From climatology?
From climatology.
Oh, okay. So these are climatological correlations.
Climatological correlations. Okay. So
They won't vary in time.
they won't vary in
Or
time
you think, okay, so you pick from the May.
because that's the way you
all
are.
May and all June and all, okay, something like that.
And also for each variable, it is going to be different.
Yeah.
So so this gets a little difficult to actually implement. Yeah. So okay. The next question is, how do we estimate observation error? Okay. See, at the very beginning, we have seen that the observation error variance and the model error variance or covariances, they are an integral part of this entire scheme of things. Okay. If your observation error is too large or if it is too small, then you are going to land in trouble. So there has to be a healthy ratio between your observation error and your model error. Okay. Now the question is, how do we estimate this observation error covariances or this observation errors, let's say? How to do that? So the observation error, it consists of two parts. One is the measurement error and the other one is called the representation error. Okay. So the measurement error, you can get it from the instruments. Whatever instrument you are using it to measure, they are going to come with some precision. They are going to tell you what your measurement error is going to be. Okay. The hard part is to figure out what the representation error is. Okay. Now this representation error, they talk about, so the nomenclature is, some people call it representation error, some people call it representative error. So there are various nomenclatures here. We'll use here representation errors, RE. Okay. So this is one work where we had kind of estimated the representation errors of temperature and salinity in an ocean. Okay. And I'm going to tell you how we did that. And also I'm going to tell you about another method where some other group, they have estimated the representation error in a different way. So now look at these plots. Okay. So in the real world, if you observe, let's say a cyclone, you are going to observe something like this, okay? But when you are trying to model it, right, using discrete grid points, you will probably, depending upon your resolution and all that, you will probably come up with something like this. You will not be able, your model will not be able to resolve all the length scales that are involved because of discretization and all that, okay? So what exactly is observation error? So the observation error is observation minus the truth. So this I can write it, whatever I have observed minus whatever the true observation should have been, okay? So yt here is the true observation and y is something which we have observed, okay? And xt is the true model state, not the analysis, not the background, nothing, it's the true model state. And h is your operator that projects your true model state into the observation space. So this one is your instrumentation error and this one is your representation error, okay? Now think of it in this way. Suppose I go into an ocean, okay, and I measure a temperature of the ocean. Let's say at a single point. It is going to give me the temperature at a particular location at a particular instant of time, right? What does my model give me? My model is going to give me at that location some average value of that model, which is averaged over some time instant. That is what my model is going to give me. So there are a lot of differences between what my model tells me and what my observation tells me, okay? And there should be a mechanism to bridge that gap, to know about what this unresolved scales, how we can kind of get an estimate of these unresolved scales, okay? So what we did here is, so suppose I have a high resolution model, okay? We will assume that this high resolution model represents the truth, okay? This is an assumption. From lack of better estimates, we'll assume that this high resolution model is reflecting the truth, okay? Then we will construct a low resolution model. For example, here, if you see these grids, these are like 1 by 12 degree grids, and then you can find another grid by these large red dots, okay? So the grid represented by these large red dots, they are a low resolution grid, and this mesh is a high resolution grid. Now I run my model at the high resolution. So I have an estimate at each of these grid points from that high resolution model, correct? Now what I am going to do, now from this high resolution, I am going to estimate my model at this low resolution grid points, okay? So I have a high resolution mesh. At each of these mesh points, I know what my model estimates are. Everybody with me? Okay. Next, I am going to choose a low resolution mesh like this. From this high resolution estimate, I am going to evaluate at this low resolution mesh points. I can do that. Essentially regridding or averaging. Okay. Next, what I'm going to do from this low resolution, I will use a simple bilinear interpolation operator to again from this I will come back to this. So I had an original value at these grid points, and then I have a reconstructed value at these grid points. Right?
Sir, in initial state, we have only y value, not yt value. So from where we get yt value? Means true observation.
True observation.
Yes, sir.
True observation we don't get.
Without
See here I am subtracting true and then adding true again. You are talking from here, right?
yes, sir, yes, sir.
So I'm subtracting the true value and I'm adding the true value also. So essentially I am not doing anything, just rearranging the terms.
After first iteration,
No, not first iteration. This is the observation error. So this observation error I have decomposed into two parts. One is the instrumentation error, which is y minus yt. Okay?
yes, sir.
And this one is the representation error, which arises because of the inability to resolve all the scales.
But to solve this equation, we need a yt.
We are not solving this equation. This equation we are not solving. I am just saying that your observation error comprises of two parts. Not only yt, you even don't know xt also. Both of these are unknown. It's just to show you what are the different components of your observation error. That's it. We neither know yt nor do we know xt. Okay? Yeah, so where was I? So now from this high resolution mesh, you already had a model estimate, and then using this exercise, you also have a reconstructed y. All you have to do between these two is take the RMSC of this across all these points, and then you will get your representation error, which will vary in space and in time. Okay? So another method is there a chalk or something? Can you guys see it from there? So this is another way in which some groups have calculated the representation error. So you have a vertical profile of a temperature or a salinity. Okay? So what you do is you calculate the gradients of that. This one?
There's a high resolution of n by n.
N over m. Yeah. N over m. N over m. Yeah. Sorry. Yeah. Okay. So all you have to, you have a temperature profile like this. So this is your vertical direction z, and this is the value of the temperature. So all you have to do is you have to estimate your vertical gradient of temperature at each locations along the curve. Okay? And this function or this expression is going to give you your representation error. This multiplied by a scaling factor. So this particular paper that I am talking of they used a scaling factor of about 0.5 degrees centigrades for temperature. Okay. So for this, you only need observation. Okay. But this also varies with time, because this profile, this is at one instance of time. This is how the temperature profile is. At some other instance, this profile will change, right? So your dt, dz and everything is going to change. So your RE is going to be dynamic. For this method, you only need observation. For that method that I talked about, you only need model. So using both, you can get an estimate of temperature, estimate of representation error. You can calculate it either from the observation or from the models. So here, I'm showing you a plot. So if you use only the observations, which is by the green line, so this is the RMSC. When you estimate your RE only with the green line. And if you do it only with the models, then the blue line is what you get, the RMS. So we see, or we have shown that using models yields you a slightly better estimate. Okay? So now we'll move on to the systems, the ocean data assimilation system that we have in place at INCOIS. So like any data assimilation system, you need three components. One is the model. In this case, the model is called ROMS, Regional Ocean Modeling Simulation System. Okay, ROMS. And then you have observations. So what are the observations that we have in ocean that we assimilate? One is temperature observations, salinity observations, then you have sea surface temperature from satellites that you observe, and then there are SLA, sea level anomaly. That also from satellite you can observe. Now you have to choose, after all this, you have to choose a data assimilation system. There are multiple data assimilation systems at place. I'm sure you have learnt about it. Ensemble Kalman filters, 3D VAR, 4D VAR, so on and so forth. What we have chosen is something called LETKF, Local Ensemble Transform Kalman Filter. So this is actually a variant of ensemble systems, Ensemble Kalman filter, and okay, we'll talk about it. So this is the model domain it comprises the entire Indian Ocean, okay, from 30 south to 30 north, and then from 30 east to 120 east. So we'll evaluate the system in this. So, and the resolution is about 9 kilometers. So you have grid points spaced every 9 kilometers apart, and then there are about 40 vertical levels, okay, in the vertical direction. It's discretized in 40 levels. Since it is a regional model, it needs boundary conditions. So it is open in this direction, it interacts with the Pacific through this direction, it interacts with the Southern Ocean, okay? So we'll have to provide boundary conditions to this regional model. Where do we get those boundary conditions from? So there is another global model called INCOIS GODAS, okay? From that, we provide boundary conditions to this regional model. Okay? Okay. Also, this ocean model needs to be forced with atmospheric fluxes. We get those fluxes from NCMRWF. Okay? Have you guys heard of NCMRWF? National Center for Medium Range Weather Forecast in Noida.
Yeah, Dr. Indra Rani was there.
Indra Rani. Oh, her talk is already over? Okay. Yeah. So they provide us with these ensemble fluxes. Since it's an ensemble system, we need ensemble fluxes also. I'll come to that. I'm not getting you. Say it again.
Which variables you are providing in boundary condition?
Okay, so so we are solving the ocean system, right? So what are the state variables of the ocean? What is the state variable? Right? Right? And the two surface currents, right? U and V. Okay? These are the 5 state variables of the ocean. So when you write an equation for each of these state variables, okay, so you will have to solve it given there is an initial condition and there's a boundary condition. Okay, that you have to provide to these equations. So for each of the state variables, we have to provide a boundary condition. Because what happens, you see, okay, no, I'll not get into that. Because, so there are boundary conditions we provide for temperature, salinity, sea surface height, and the currents. Not only at the surface, but across the depth as well. Okay? Here, the temperature should know when you are evaluating what is the temperature here, just south of this. Okay? So that information is provided by inchoate godas. Okay? Okay. So ये तो model हो गया. Now we know about the model. What about the observation? What are the kind of observations that we assimilate? So this is just we assimilate temperature, salinity, and sea surface temperature. So temperature and salinity we get from various platforms like Argo floats. Do you guys know about Argo floats? All of you? Okay, so Argo floats are instruments which they deploy in ocean. What it does is every 10 days or so, it pops up from about 2000 meters to the surface. Okay? From 2000 meter, it will pop up to the surface, and while popping up, while coming from subsurface to the surface, it will measure your temperature and salinity. Okay? So essentially, it is measuring the entire vertical structure of the ocean. And once it comes to the surface, it communicates that measurement through a satellite. Once it communicates, then it will again go down. It will drift for another 10 days and then will again pop up. So this is repeated. These are called Argo floats. Okay, there are hundreds of Argo floats in the Indian Ocean. Okay, then there are other observation platforms called mood buoys. Mood buoys are something which are in situ observation. It is going to be there, installed. It will not drift. So it will provide you, again, a vertical profile of temperature and salinity at a singular point, okay, every day. Okay? So these are the kind of observations that we assimilate, in situ observations. And then there is another observation which is from satellite. So the satellite measures the sea surface temperature and relays it to us. So we assimilate the sea surface temperature over the Indian Ocean as well. Okay, so there are 3 variables that we assimilate: temperature, salinity, and SST. Okay. Which one?
Kutty and Argo.
Argo, I told you, it pops up every 10 days. Okay, but then you have to understand that some Argos pop up on January 1, some different set of Argos pop up on January 2. The one that has popped up on January 1 will again pop up on January 11. So all of them do not synchronously pop up. Each Argo has a 10-day cycle of popping up. But each Argo is initialized on different days. So each day you have profiles from some Argos. Is it clear? Okay. So these are the various observations that we assimilate. What is the data assimilation system? The data assimilation system is called local ensemble transform Kalman filter. So this paper is the paper on LETKF. Okay. So what it does, it also minimizes the same cost function that I'm sure you guys have been studying over here. This is the same cost function, right? But it does so in a local space. Also, whatever happens over the ensemble space. Okay? So there's a model space, there is an observation space, there's an ensemble space. In our case, since we are working with 80 ensembles, so our ensemble space is 80 dimensional. So essentially, whatever is happening localized and is happening over a low dimensional space. Because of this is very fast compared to a normal ensemble Kalman filter system or ETKF or EAKF. LETKF is very fast. Okay. So what are the salient features of this? So we have around 80 ensembles. So any ensemble system will need ensembles. We have about 80 ensemble members. So 80 different versions of the same model, like 80 different initial conditions. Okay? This is our ensemble to start with. Okay? We'll tell you how we got those 80 different initial conditions, but 80 setup of ROMs, let's say.
Sir, how do you perturb on the basis of time or some parameter?
What I have not perturbed anything as of now.
So, by initial condition, how?
I'll come to that. Hold on. Okay. Now, most of the ensemble systems, they suffer for something called filter divergence. Do you guys know what a filter divergence is? Okay, filter divergence is very simple. What happens is all your ensembles, you start with different ensembles, meaning with a spread in your initial conditions or your model states. Okay? As you start your data assimilation and as time progresses, that spread decreases, keeps on decreasing, and eventually it collapses. So all your ensemble members, what happens is it becomes something very similar to each other. Okay?
This they should have seen. They executed the. So I had a Python notebook,
Oh.
which on Doris 96.
Which means they haven't done that.
Well, this was my difficulty as well. That I'm not sure what they have seen and what they have not seen from their faces. So.
Yeah. So.
Please be responsive about what you know. Very useful.
So I'm assuming that probably you don't know. So what happens is that all these ensembles, they collapse and kind of become identical to one another. Okay? So what happens when this ensemble spread becomes very small? We've gone through that. Your model error becomes very small. Model error variances. bias. We talked about observation error covariances, model error covariances. What happens when our model error variances are very small compared to observation error covariances?
Our analysis will be very close to our estimated model estimate. That is the ground we are using.
Thank you. So you will have a lot more trust on your model, right? Your spread in the ensemble actually signifies the kind of uncertainty is there in the system. Okay. Now, if that spread decreases, then you are having more and more and more trust on your model. So when an observation comes, all you will do is you will throw away that observation. You'll say, I do not trust the observation. I trust my model more. So the entire purpose of data assimilation gets defeated. Right? So most of the ensemble systems, they suffer from something called filter divergence. This is called filter divergence, collapse of the ensembles. Okay, and then we need to take measures to avoid this. And various data assimilation systems, they take various measures. Covariance inflation is one such measure. In this system, what we saw is that even with covariance inflation, okay, we could not manage to arrest filter divergence. So we had to resort to other means. So what have we done? We have used two different kinds of mixing schemes. Okay, so what are mixing schemes? Mixing schemes are actually parametrization schemes in which you are going to, okay, so what happens is when wind blows over the ocean, okay, you have convection. It blows over the ocean, the dynamic starts, then water starts to mix in the vertical direction. How it is going to mix? Okay, that is given by these mixing schemes. So there are various mixing schemes out in the market. So we have chosen two different mixing schemes. Okay, since we have, okay, I'll come to it. So we have chosen two different mixing schemes to kind of arrest filter divergence. Also to run a model like ROMs, it comes with parameters, right? Like what is the diffusivity coefficient? What is the viscosity coefficient? All these parameters it comes with. So we have used different parameters across different ensemble members. Okay. Then we have also used the spatiotemporal representation error in the previous slide that we have seen. We have also used that. Using all these measures, we eventually managed to arrest this filter divergence, this collapse of these ensembles. Okay, we could see that the ensemble spread is kind of steady after all these measures. Okay, and the other thing is we assimilate every 5 days. Okay, so suppose today is May 15th. Whatever observations are there on May 15th, we assimilate. Okay, we get an analysis. With this analysis as the initial condition, we again run the model. Okay, we run it for 5 days. Now we come at May 20th. On May 20th, whatever observations are there, on May 20th, we ignore the previous day's observation, May 16, 17, 18, 19 to ignore. Whatever observations we get on May 20th, we again assimilate. we again get an analysis. With this analysis as the initial condition, we again proceed forward. This is how it goes on. Okay? So the assimilation window is every 5 days. If any of you need this reanalysis of the Indian Ocean, we have it from August 2016 onwards. Just drop me a mail that you need ocean reanalysis of the Indian Ocean for this period or so. Okay? My mail ID is aryapaul@incois.gov.in. Okay? In any case, if you need it, maybe not now, in future, you can always drop me a mail to get this. Okay? So the ensemble collapses, but the filter diverges. Your Kalman filter. What was that? Oh, So essentially what happens is your XA becomes XB. Okay? This is your filter, PH transpose H, this inverse. Okay? This becomes infinite. And this becomes 0. The second term, this term becomes 0 because this diverges. Okay? That's why it is called filter divergence. Either you can say filter divergence or ensemble collapse. कहाँ थे हम लोग? Yeah. So from other data assimilation systems, what this data assimilation system is different from is there are two things. Okay? One is use of this spatiotemporal representation errors. Most data assimilation systems do not have a spatiotemporal representation error in their system. Okay? The other novelty is use of two mixing schemes. So I have 80 ensembles. So I divide 40 ensembles, I divide it into two. So the first 40 ensemble members, they have KPP mixing scheme. The other 40 has Mela-Yamada mixing scheme. Okay? Then there are combination of model parameters like diffusivity and viscosity. They vary across these models. Okay? So the point is that combination of all these schemes, okay, help us in arresting the ensemble collapse and getting a healthy spread. Okay? Now, okay, so
This RMS that you are showing, respect to what?
this, which one? This RMSD? This with respect to observation. This SST, this is most likely with respect to GHR SST.
Assimilated or not assimilated?
Not assimilated. Some other, so there are various satellites, a different satellite. So, yeah. See, you guys, I'm assuming all of you were there in Professor Varahan's class, right? So one of the primary requirements of data assimilation is that we will start with a Gaussian distribution or error covariances and all that has a Gaussian structure, right? You guys remember? So the problem is when you use two mixing schemes, okay, what happens is that your Gaussian or your unimodal distribution, this, it becomes this, a bimodal distribution, because you are using two different mixing schemes. You can see it here. See, this is the distribution that we started with, the black one, okay? Because of this KPP and Valiamala, two different mixing schemes, my distribution has become, which one? So this blue one is, if I simply let, without any assimilation, two models, one with KPP and one with Valiamala to run. So one peak is for one mixing scheme, the other peak is for other mixing scheme. So the problem is that I am violating, right, that constraint of Gaussian distribution. If I do this, can I? As it turns out, is that after assimilation, I am getting a distribution like this. Not perfectly Gaussian, but something which is close to Gaussian. This dotted black. Okay. So yes, it is not strongly constrained to be a Gaussian, but it is kind of a weak constraint to be a Gaussian system. And this is kind of a trade-off, that okay, I will move away slightly from the strong constraint of Gaussian distribution, but then I can also arrest this ensemble collapse or filter divergence. Okay? See, look at this ensemble spread. So this is an ensemble spread of 2 years. Okay? This one is at the surface, the blue one, and the red one is at the subsurface. So what you can see is that the ensemble spread is not constant, but it has not diverged too much, neither has it collapsed. It is kind of maintaining a steady value after whatever we have done, all this, mixing schemes, this, that, after all this, okay? So these are the kind of analysis, like just to show that how this system behaves. So this is the Taylor diagram. You guys know Taylor diagram? How it is to be read? Anybody who does not know? Oh, okay. Okay, so these kind of diagrams are called Taylor diagrams. Okay. Now, how to read this Taylor diagram? For example, you take this point. Okay, this corresponds to something called a free ROMs where no assimilation has taken place. So this green dotted lines, they are the RMSC. So this green dotted line is 0.4, this one is 0.6. So this one has an RMSC which is slightly larger than 0.4 but less than 0.6. This is between these two arcs, right? So it has an RMSC of about slightly larger than 0.4. What about the correlation? Okay, so this model has a correlation somewhere between 0.7 and 0.8. Okay, this red one is the standard deviation of the observation, this red arc. Okay, so this one has a standard deviation of what? More than 0.6. So this observation has a standard deviation of something, let's say 0.4, 0.48 or so, little less than maybe 0.5. But this has a standard deviation of more than 0.6, maybe 0.62 or something. This is how you read a Taylor diagram. Clear to all? So now, so this one is for a model which has not assimilated anything. Now this is our model, this solid red dot. So this model, if you see, has an RMSC which is less than 0.2. This has a correlation which is slightly less than 0.95. Okay? And this one is very close to the standard deviation of the observation. Correct? I hope in future all of you will be able to read Taylor diagrams. Okay? Now, how do you, let's say, troubleshoot or analyze your results? Now look at this. So this is SST, okay? This is correlation of SST from LTKF ROMs with some observation. This is from free ROMs, no assimilation, and this is the difference. So the difference means LTKF minus the free ROMs, okay? Now this one, red patch means that assimilation has improved. Red patch means positive, which means this correlation is higher than this correlation. And blue patch means there has been some degradation after assimilation. So what we see here is across the North Indian Ocean, in majority of the places, it has improved, right? But there is a slight patch given by this R2 region where it is negative, where it has, for some reason, it has deteriorated. The question is, why has it happened so? Why did it not improve here as well? So to understand this, what we have done is here, we have plotted the observation density over R1 and over R2. Okay, the number of observation, the average number of observation within this across time. What we see is that over this region, R2, okay, the number of observations are very limited compared to the number of observations that we have over R1. So most likely this is the reason why we do not see an improvement or rather a degradation in this region, but just north of it, there is so much of improvement. Okay? Now current, so when you kind of, for zonal current, so this is similar. This is the correlation from our assimilation system. This is the correlation from the non-assimilated system, and this is the difference between these two correlations. Red means good, blue means bad. This is the RMSC from our assimilation system. This is RMSC from our free system, no assimilation. And this one is difference between this and this. In this panel, blue means good, negative, okay? Blue means good and red means bad. So what we see here is that our assimilation has improved the surface current estimates across most of the region. Okay, there are certain patches like here and so, where there are some degradations, but over most of the region, it has decreased the RMSC. It has improved the estimation of the surface currents. Okay. Now this is in the vertical. So there are some things called ADCP, okay, acoustic Doppler current profilers. Those are stationed at one place, and what they do is they measure currents at certain depths. So here is those currents at this depths. Okay, so this is the observation. This is what you get when you do not assimilate anything. So these large, intense currents, okay, when you do not assimilate, these become more intense. Remember, we are not assimilating currents. We are only assimilating temperature and salinity. Okay, but we are looking at currents here. But this one, which is after assimilation, what happens is that it reduces the intensity of these currents and tries to bring it closer to the observation. Here also see, here there are no intense currents, but this free model has a very intense current here. With assimilation, it has reduced the intensity of this. So, which means that assimilation is kind of working. There is another called HF radar system. Okay, observation system, HF radar. What it does, so you kind of install it at the coast, and it has a very limited range of, it only has a range of about 200 kilometers. So install it in the coast, over a circle, it is going to measure your surface currents, and that too at a very high frequency, every 15 minutes or so, and spatially also every 200 meters, if I am correct. If I do not, yeah, I think every 200 meters, it will measure your surface currents. So here also, we have done a similar exercise, and we have seen that there is a large improvement in the currents. So here red means good, blue means bad, and here blue means good. So this is difference in RMSC, this is difference in correlation. Okay. So the next question here that we want to, okay, so before I move on to this, I forgot to answer your question. So how do we select our initial ensemble or the initial spread? So for any data assimilation system to work or any ensemble system to work, you ought to have a initial ensemble. So your 80 ensembles will have different initial conditions to begin with, right? But how do you choose those 80 different conditions? What is the mechanism, methodology to do that? Okay? So what we have done is we have run our free model, no assimilation, nothing, for a very long period of time. Okay? For around 40 years or so. Okay? We planned to start our data assimilation from August 2016 onwards. Okay? So for previous 40 years, since we have run it, we have the ocean conditions for the last 40 years of August. Okay, that we can store. So when you are running the ocean model, what we have done is we have stored the August conditions of the ocean over the last 40 years. And if you store it, let's say on 1st of August and on, let's say, 15th of August. Okay? For each such year, you have 80 such states for the last 40 years. Correct? With those 80 states, we have initialized those models. We have not perturbed or done anything, no perturbations. Okay? So this is how we have initialized our ensemble system. So any questions as of now? You guys have been very passive. Yes, please.
The SST goes into the simulation. So, is it the satellite SST only or the Kutty SST?
Okay, so it is the satellite SST. So when we say that SST goes into the assimilation, it is the satellite SST. So there are certain practical problems that I would like to highlight for you guys. Maybe there is, so the SSTs that we get from satellite, they are of very high density. Okay, so you get SST about every 1 kilometer or so. Whereas our model has a resolution of 9 kilometers, right? So this highly dense sea surface temperatures, should we use all this dense observation, or there is something called, people say, data thinning. Have you guys heard of this? Huh? Data thinning, or people also call it as super robbing. Okay, so what people do is that, or we also do, is these highly dense observations, we kind of coarse grain it. Coarse grain it in the sense we kind of average it out. We do not take all the observations that the satellite provides. Okay, that will actually make your observation vector too large. So this, if you choose to take all these observations, first of all, your observation will be of the order of 10 to the observation, the length of the observation vector will be of the order of 10 to the power 6 or so. Okay, so one, and then we do not need those many, because anyway the model does not resolve those scales. So what we do is that we thin those observations, we do a super robbing. By super robbing, we mean we do a coarse graining, or let's say a data averaging, and we choose the average value over a certain region. Let's say over a 1 by 4 degree by 1 by 4 degree. We construct a box like that, and we choose the average of that, and then we pass it on to the data assimilation system. So this is called data thinning. You do not need all those many observations. This will unnecessarily complicate things, becomes computationally more expensive and things like that. So before I proceed, OROMs is nothing but a free ROMs. So where you do not have any assimilation. That's it.
So we are comparing one example output with another model, and then we are comparing it.
Yes, yes. So this is, so all this is saying is what are the improvements due to assimilation. So both these systems, the models are same, it's ROMs, okay. In one you have assimilation, in the other you do not have assimilation. So what happens, what are the improvements you see, or if there are any degradations once you put assimilation into place. This is what it is showing. Okay.
So how do you get the surplus from 40-year
I told you we are storing the model state twice every month, twice in the month of August. So from each August we are getting 2 model states. So from 40 August, 80 model states. Okay, so the next question we will address is is it always good to assimilate observations or all available observations? So during tea time, give it a thought that should we always assimilate observations? If yes, why? If not, why? So this is outside the purview of this data thinning or superverbing that we talked about. Okay. So let's say I have no satellite observations. Let's say I have only these buoys and Argos and things like that, in situ observations. Okay. The question that I am asking to you guys is it good to assimilate all those in situ observations always? Just give it a thought. Okay? Can we break? It's 11 o'clock.
So let us thank Dr. Arya Paul for his excellent talk on ocean data assimilation.